Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinars. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. We have a great event on tap as always, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you will have the opportunity to access it later. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question for either of our speakers, please don't wait, don't hesitate, just use the question and answer tab there on your interface and submit your questions, and we'll try to get to as many as we can near the end of today's webinar. We also have a very interactive chat feature, so I do encourage you to chat as your questions, comments, suggestions, whatever you got, go ahead and send it on over, and we'll keep an eye out for your chats, and we might even chat you back. And then at the end of today's webinar, we are doing a drawing for 4 $100 Amazon gift cards. So please stick around. Hopefully you will be one of our 4 lucky winners. All right, with that, let's go ahead and kick off today's webinar, which is Cloud Native Disaster Recovery with YugabyteDB and OpenShift. Our speakers today are Hemant Banawat, who is the Director of Engineering Performance at Yugabyte, and Raphael Spazzoli, who is the Senior Principal Architect at Red Hat. Gentlemen, thank you so much for joining me today. Great to have you here.
Thank you.
So Raphael, I know you're going to be kicking off the conversation. I'm going to take myself off camera, put myself on mute. I'll see you when we get to the question and answer period.
Thank you very much. Yes. Yeah, can we go to the next slide? And welcome everyone to this webinar on cloud native disaster recovery with Yugabyte and OpenShift. The plan today is to talk about, share some ideas on cloud native disaster recovery, then go a little bit more in depth on how you can implement these deployments and disaster recovery strategy with YugabyteDB. And then finally, we have a demo at the end of actually implementing this architecture with Yugabyte and OpenShift. So we would like to start with cloud native disaster recovery. This is a concept that we are defining and working on in the CNCF tag storage. There is a white paper if you're interested in going in depth. Today, we're going to stay high level, and I'll give you a definition of it. I'll use this table to give you the definition by contrasting cloud native disaster recovery with the traditional disaster recovery strategies that you see in many enterprises. This, by traditional here, we mean the average enterprise, right? Not the unicorns, not the web scaler. What we find in an average large enterprise. Another thing before I start on the table is cloud native disaster recovery is not a new idea, but what we want to submit to your attention is that using cloud native approaches, we can actually now implement these strategies with moderate costs and relatively easily to configure deployments. So let's start with this, going line by line on this table. The first aspect that we want to highlight to see this difference is the type of deployment. In traditional disaster recovery, what you normally see, especially for stateful workloads, is active-passive type of deployment. Very rarely, enterprises have the ability to do active-active, where multiple data centers, or maybe if you're in the cloud, multiple regions can serve traffic. In cloud native DR, we want active-active deployments. And then from a point of view of how do we detect that there is a disaster going and how do we trigger the recovery strategy, in traditional DR, we normally have a human decision. But for cloud native DR, the software needs to be able to detect the problem and autonomously react to it. And then when it comes to executing the disaster recovery procedure, in traditional DR, we see very often that there is a mix of manual and automated tasks. So perhaps I have to start up some machines, some data is being transferred to another data center, and then applications are being deployed. In cloud-native DR, the recovery procedure has to be automated. So the software has to both detect that there is a disaster, there is something going on, and has to react and execute the procedure. And then coming to the main metrics of a disaster recovery strategy, which are RTO and RPO, which respectively represent the length of time that your service is not available and the amount of time for which you lose transactions. So it's a measure of consistency and the amount of data that you lose during the disaster. So for RTO, we usually see from 0 to 2 hours of outage in traditional DR, depending on how much you have invested in the recovery procedure. But normally, when there is a human decision, just making the decision can take hours. And then in cloud-native DR, we want this metric to be close to 0. It cannot be exactly 0 because usually the global load balancer that will send traffic to the LT location has some timers internally to react. But besides that, so it's going to be a matter of seconds, maybe 15 seconds before you can of outage that the external clients observe. And from a recovery point objective, again, depending how you have organized your data, you can go from 0 to hours. If, for example, if you use backup and restore, you're going to have the frequency of your backup and restore is essentially your RPO. For cloud-native disaster recovery, we want you can get to exactly 0 if you're using strongly consistent deployments. Today, we're going to give a demo of a strongly consistent deployment. And if you're using eventual consistent deployments, then you are theoretically unbounded RPO, but in practice, again, close to 0. From a perspective of who owns the disaster recovery procedure, in traditional DR, the business continuity plan is owned by the applications. But what they do normally is they turn around to the storage team and ask them what their SLAs are. And de facto, the storage team owns the procedure. In a cloud-native DR, because most of these automated procedures depend on the middleware software, and the middleware software is owned by the application team, the application team is the actual owner of the disaster recovery procedure for their specific application. So they have to pick the right middleware, and they own the procedure. And in terms of what technical capabilities enable us to create our disaster recovery procedures, traditionally, these capabilities come from storage in the shape of backup and restore or volume replication, whether it's synchronous volume replication or asynchronous volume replication. But in cloud-native disaster recovery, what we really need are capabilities that are coming more from networking. So we need east-west communication between our availability zones, whether these are data centers or cloud regions. And then we need a good global load balancer in front of our deployments that's smart enough to detect when there is a disaster going on. If you're interested in going deeper in this definition and then all the theory that is behind it, you can click on the link here. And when we share the slides, and that will take you to the white paper. Next slide, please. This is one of the things you can find in the paper, in the white paper. This is a reference architecture of a cloud-native disaster recovery deployment. In it, you can see that there is a stateful workload, and each instance of the stateful workload has its own volume. But the synchronization happens at the workload level. So the stateful workload instances, they cluster up and they talk to each other. So that's why we need that east-west communication. And they keep in sync. And then on top of that, we can imagine that we have a front end, a stateless front end, and in front of the front end, we have a global load balancer. And again, this global load balancer, when one of the data center goes down, needs to be able to detect that and to redirect all the traffic to the healthy data centers. Next slide. So in the white paper, we go in depth about the concept of replicas and shards or partitions, which are the basic concepts that all of these distributed middleware, distributed stateful workloads use to organize themselves. And this table summarizes some of the research that we have done. We have taken all of these products, we have analyzed what they use in terms of replica consensus. The most popular here is Raft, and what they use in terms of shard consensus. And you can see here, Yugabyte, more or less in the middle of the table, uses Raft for synchronizing the replicas. Obviously, we need to replicate the data to make sure to have redundant data and make sure that if we lose a location, we still have access to the data. But also we need to synchronize our shards to be able to do inter-shard transactions. For shard synchronization, two-phase commit is the protocol that Yugabyte uses. Next slide. Another thing that you can find in the white paper is a reference architecture for Kubernetes deployment. So from the general reference architecture that you saw before, which you could use to deploy on virtual machines if you wanted, we zoom in on two containers and Kubernetes as a container orchestrator. So the architecture is not that different. As you can see, we still have the stateful workload. This time it's a container. It's running as a pod inside of Kubernetes. It still needs that horizontal east-west communication capability. So here there is a problem to be solved because making those clusters communicate horizontally. It's a capability that depends on your Kubernetes distribution. And then on top, you can still have a front end. You will have an ingress to get into the cluster. And then again, we need a global load balancer. And then we also analyze what happens not just if you lose an entire data center. That's relatively easy when you have a strong, consistent workload. The other element of the cluster will reorganize itself. But we also analyze what happens if there is a network partition between the instances of the workload that does not affect the the communication from the client, so from the global load balancer. And here, for a strongly consistent deployment, in this situation, the workload, the partition that doesn't have the majority of the instances will set itself into essentially offline mode. So eventually, from the global load balancer point of view, that data center is offline and the behavior is the same as when you get a real disaster. Even in the case of just a simple network partition. The behavior, we also analyze the case of eventual consistency. It's not here in these slides, but you can find it in the white paper. And in that case, the behavior is different, and there are some additional considerations. Next slide. And I think now I'm on turns to go in depth into Yugabyte, and now it solves it can support the architecture that we have just seen.
Sure. Thank you, Rafael. I am Hemant Banawat. I work at Yugabyte. Yugabyte is a distributed SQL database. It works on multiple nodes, and it's kind of a distributed database which is highly consistent. In fact, strongly consistent. It is an open source project, and it comes with a Apache v2 license. We are also part of CNCF community. So that's a bit about YugabyteDB. But in this presentation, I would be talking YugabyteDB primarily in the context of cloud native architecture and disaster recovery scenarios. So to start with, let's talk a little bit about the traditional RDBMSs and their disaster recovery. I mean, how the disaster recovery is handled in with traditional RDBMSs. So here in this picture, you see there are microservices that are running across different regions, and you have a RDBMS that is running in region 1. All the microservices are accessing the data from this instance of RDBMS. Now, for the disaster recovery scenarios, in case the region 1 fails, we also maintain a passive replica of this RDBMS in a second region, right? Now, this is a very standard deployment, a very standard topology. I think Rafael also talked about it. So in this case, all the reads and writes still go to the master node, which is running in region 1. However, all the changes that are coming into the master are also getting asynchronously replicated to the passive replica. Now, when you have this kind of model, in case of a disaster recovery, when the region 1 fails, the passive replica automatically becomes the master in this case, right? And it will start taking all the reads and writes from all the running microservices, right? However, there is a temporary data loss during the failover. I mean, consider this scenario: you write certain data to your active master, which was in region 1, and before it could replicate the data to the passive replica, because the replication is an asynchronous replication, before it could replicate, it went down. Now in this scenario, although the passive replica becomes the active master, but it does not have the latest copy of the data, and what applications might see is a little older copy of the data, right? So that is a data loss that might happen in this particular topology. There is another topology that comes with traditional RDBMS, which is worth mentioning. It is a multi-master model. So in this case, you have two instances of the database running in two different regions, and your microservices in each region are accessing the local master, right? Local master. The local replicated replicas, that is for the disaster recovery within the region. However, the important part in this particular scenario is a conflict resolution, because both masters have to maintain the same copy of the data. There has to be a conflict resolution that happens between these two masters. Now, when you have a conflict resolution happening between these two masters, there is a guaranteed data loss when the same row is updated for both the masters. For example, your application in region 1 adds $100 to your account, and also at the same time another application in region 2 also adds $100 to your account, right? You will end up having only one of this. If these two transactions come in at the same time, you will end up having only extra $100 in your account instead of $200, right? So that is a challenge that we have with a multi-master model with traditional RDBMS. Okay, so now jumping to YugabyteDB. YugabyteDB is a distributed database, as I told you. The data is automatically sharded. I mean, since Yugabyte runs across multiple nodes, the data is automatically sharded across different nodes. We also call these shard as tablets. So tablets and shards in Yugabyte context are used interchangeably. So now for every tablet or for every shard, you have one as leader and rest are the followers nodes. There is a consensus that happens between the leader nodes and the follower nodes for the writes that happen. The consensus is the draft consensus algorithm that we use for between these nodes to replicate the data from master to the from leader to the follower nodes. Now, each shard has, as I already told, each shard has one leader, and there can be n number of replicas based on the topology that you are going with. The data is also continuously rebalanced as the nodes are added or removed in this scenario. However, whatever may be happening inside Yugabyte deployment to the end applications, to the applications that are accessing the database, it is a single logical relational database, and all microservices get is an endpoint to which they can access, like they would be accessing any Postgres or MySQL endpoint. So Yugabyte is a strongly consistent distributed database. It has a, it has a concept of failure domains. What that means is that what is a failure domain? I mean, you would like to distribute your data between failure domains so that you can handle failures. For example, if you distribute your data between 3 failure domains, and if you lose your one failure domain, the data would still be available for the applications that are trying to access it, right? You can define your failure domain as a region or a availability zone or even a rack, right? So those are the things that you can define as failure domains based on what kind of topology you want. And Yugabyte will take care of replicating the data across various failure domains so that the end applications always get a consistent view of the data in this distributed environment, right? With Yugabyte, the recovery point objective is 0. What that means is that Yugabyte is a strongly consistent database, and uh, whatever kind of failure might happen, it will still give you a consistent view of the data. Right? So that is why Yugabyte has a recovery point objective of exactly 0. The recovery time objective with Yugabyte is of about 3 seconds. What that means is that in case of a failure, the read or write request might fail for a maximum of 3 seconds, right? So in case of a disaster scenario, the recovery time objective is 3 seconds with Yugabyte. Just to elaborate a little bit, in this example, see in front of you have the failure domain as a zone. So you have data distributed across 3 failure domains, which are zone in this case. Now let's say a particular zone goes down. So the zone B goes down. In this case, the tablet leader, which was earlier on node 4 and node 6, are moved to the node 7 and node 2 respectively, right? Now, when you move these tablet leaders to the other zones, there is a time gap during which the writes and read will have to be retried. And that time is of 3 seconds. But whatever might happen, the data is always consistent, and you will always get a consistent view of the data, and it is strongly consistent. You will not lose any data during these kind of failures. Yeah, so so YugabyteDB, I think, as I already said, there is no data loss whatsoever, and along with that, Yugabyte also, supports multiple topologies. So with multiple topologies, you can always be sure that there will be no data loss. For example, in this scenario, you have 3 different topologies. You have in the first topology, you have a single region and multi-zone. In second topology, you have the data distributed across single cloud, across multiple regions in a single cloud. And in the third one, the data is distributed across clouds and across regions as well, right? Now, in all the 3 topologies, I already said the data is going to be consistent. That is not a challenge with Yugabyte. However, in first scenario, there is no cross-region latency. Since they all belong to the same region, you don't encounter any cross-region latency with this first scenario. But there is, in case of a region level failover, you will lose data because data is present only in a single region. While in the second and third case, the data would still be available if you lose a particular region, because the data is still available in other regions. However, there is a cross-region latency because the reads and writes might have to travel across different regions to fetch the data or to write the data. Right. So this cross-region latency is an issue. Cross-region latency is an issue, and how to reduce this cross-region latency is a question, right? With YugabyteDB, you get multiple building blocks with which you can reduce the cross-region latency. Also, there are certain advanced configurations which can be used to reduce the cross-region latency. I will talk about few of them here. For example, this is a case. In YugabyteDB, we have a concept of leader leases. What that leader leases means is that at any given point in time, only one of the shards, one of the replica of the shards can become a leader. Right? So a shard is replicated across different regions. Now, only one of these can be the leader at any given point in time. And this is something that we ensure using the raft consensus algorithm. And we make sure that any given point in time, only one has got the leader lease. Right? Now, what that means is that your queries whenever the read query that comes in, it has to go to only the leader node to fetch the data, because now the leader node, since it has got the leader lease, we can be sure that leader has got the latest copy of the data. It will never serve the stale data, right? So for read, we don't have to do a consensus to check that what is the latest copy of the data. Anytime a read happens, we give the copy out from the leader. And since we don't have to now do a consensus across regions during reads, the read queries become extremely fast. Right. So that is one of the important features with Yugabyte. This is another advanced configuration that we support, which is a row level geo-partitioning. In this case, you can add a column to your schema, or most of the time you already have a column in the schema, which indicates, using which you can do the partitioning of data. For example, you might want to partition the data based on the country code. Because let's say all your applications that are accessing the data that is there in the US East, all the applications running in US East are accessing the data that is for the US East, right? So you would like to pin your rows to the nearest geo/region they reside in, right? However, even though you are geo-partitioning the row, there is a single view of the table wherein all rows can be listed as well, right? So what happens is that when you geo-distribute the data, any application that tries to access the data from US East, and they try to access the data that is that has the column country code as of that of US East, it will not have to travel to any other region. The read request can be returned directly from the local leader tablet, because we have ensured that the data is partitioned, and for US East, the data remains in the US East. Another option using which you can avoid the cross-region latency is by allowing the follower reads. When we say follower reads, what it means is that for every shard, we have a leader and we have multiple followers. You always go to the leader to read the latest copy of the data. But if you try to read from the follower, you will always get a timeline consistent copy of the data. But that might be a slightly stale, right, as compared to what is there on the leader, right? However, let's say if you try to access some data for which the leader is in US Central and the application is running in US East, if you try to read from the follower, which is there in the US East, and don't go to the leader in US Central, you would be able to service that request very quickly, right? So that is a topology that is supported with Yugabyte, and that can give pretty good results if you are okay with slightly stale data. Another important aspect that we have is that of preferred regions for shard leaders. What we can do is that, for example, if all your applications, you already know that all your applications are running in US East, you can pin all your leaders to the US East region, right? You can pin all your leaders, so all the applications will fetch the copy of the data from the local tablet only, and it will not have to do a cross-region communication, and so the reads will become extremely fast, because no cross-region communication is happening, right? So you can pin all your shard leaders to a single region, and that will make your read request extremely fast. Yeah, so I discussed few of the techniques already here, and there are like these different techniques that one can use to reduce the inter-region communication and remove the inter-region latencies, right? I think I discussed few of them. There are a couple of more. For example, we have these topology aware SQL client drivers. So what that means is that, I mean, in normal scenario, what happens is that a client driver will talk to a machine, and that machine will communicate to the leader where the data resides, and then the data is returned or written, right? So there is an extra hop that happens, and this extra hop can cause the cross-region latency as well. To avoid that extra hop, we have these topology aware client drivers, wherein the client driver already know that which node it should go to, right? It will know the leader of that data, and it will directly go to that particular node and fetch the data for you. Right, so that is another important thing. Then we support multiple these configurations, these advanced topologies like read replicas. Read replicas are nothing but you have another running instance, another running nodes of Yugabyte who are just follower replicas. They can never become leaders, and they are just there to satisfy the read request. So the read replicas can be extremely fast. Also, then there are these multi-master deployments. You can have a multi-master deployment wherein the conflict resolution is done by Yugabyte itself. So those are the advanced configurations that we support. Yeah, I think that's a bit about YugabyteDB. We will see some of it when Rafael goes to the presentation, and how it works inside the OpenShift, and how the disaster recovery scenario works with these kind of things. Over to you, Rafael, for the demo scenario.
Okay, thank you very much, Hemant. So for today, we wanted to bring everything together, the theory that you heard at the beginning about how you can build a cloud-native disaster recovery strategy, then and the capabilities that Yugabyte has with a deployment across multiple regions. And then we want to simulate a disaster and show you how Yugabyte reacts to it. So let's talk about the scenario a little bit. We have 3 AWS regions in North America, in which we have 3 OpenShift clusters. So here you can see in the picture, you have cluster 1, cluster 2, cluster 3. In it, we have Yugabyte running. And if you look at the slide, the picture on the right, there are actually 3 instances of Yugabyte in each region. And so for a total of 9 instances of Yugabyte. And Yugabyte is a horizontally scalable database. You can create as many instances as you want. And the more instances, the more throughput it can handle. And then we have a east-west communication capability. Here it's between the cluster. It's realized with a product called Submariner. It creates a tunnel between the OpenShift software-defined networks. And then in front of it, we have a global load balancer. Here I have the Google Cloud icon, but today we are deploying on AWS. I have this demo. I have the capability of running it in any of the cloud providers, but for today it's AWS. And then behind the scene, we have a control cluster that I use to manage the OpenShift cluster and to easily create and configure them. This control cluster runs a product called Red Hat ACM, which is our multi-cluster management console. So one thing to point out, if you look at the picture on the right, we have a very distributed deployment across regions, multiple OpenShift cluster, multiple Yugabyte instances. But all the Yugabyte instances come together to create a single logical database. It's a single, from the point of view of the consumer, is just one database. Okay, now, so this is the setup. Next slide. And our disaster recovery simulation, disaster simulation, then hopefully we recover, is as follows. We are going to create a network isolation for an entire region. So we're going to take the entire region offline. Well, our partition of the region, not obviously not AWS region, but our VPC. It's going to be offline. And then we're going to observe what Yugabyte does. And we're going to do all of this while we are generating load on the cluster. So we are generating SQL reads and SQL writes. So insert, update, selects, using a client that is called the TPCC client. TPCC is a standard performance test tool for SQL databases. So I use it also to measure the performance of this deployment, but today we're not interested in performances. We just want to observe the behavior of the cluster, and we need a client to generate some load. Okay. So I'm going to take control of the screen and start the demo. All right, so we have, this is Red Hat ACM, like I said. We have a view here of the clusters that exist. And we have 3 clusters here. And then they are in different regions. And I have the clusters also running here. I can see that I have, so this is the console of one of the clusters. I have Yugabyte deployed. Okay. I can access the Yugabyte console and see that I have three masters. And then if I go to the nodes, I can see that I have 9 nodes, and they are distributing the workload. So we have 792 tablets, and this one, for example, has 264 leaders of those 792. We will have to follow these numbers when we do the recovery simulation to understand what happens. Okay, so now I'm going to start generating load. I have here three commands that are ready. These commands will tell a pod that is inside each of the cluster to start sending those TPCC TPCC workload. So let's start here. It takes a minute to warm up. It's creating this. The way the TPCC test works is that it creates a number of virtual users, which are called here virtual terminals, and then it simulates users working on I think it's like a warehouse kind of applications, so kind of database, so where we have orders and fulfillments and all of that stuff. So it's now warming up. Each of these pods generates 3,000 terminals. So we are running, in this case, we're in the TPCC 1000, which means we're running 1,000, this test 1,000 times in parallel. Depending on the size of your deployment, you can even go higher than that. So it should be almost ready. And in the meantime, we should start to see some. I'm going to zoom in a little bit for the last 30 minutes. And we start to see some load coming in for the database. Okay. So at this point, all of what we're doing today is going to be compressed in time because we don't have a lot of time. But so let's imagine our database has been up for a while and there is work being done on it. We are now going to generate a disaster. Okay, so I have this set of commands to isolate region number 3. What this does is essentially it creates a network rules that denies everything. So what we expect, before I change view and we go to look what happens, what we expect is that cluster 1 and cluster 2, the clients keep working, and perhaps some of the transaction time out, and perhaps they have to do some retries, but overall they will keep working. Client on cluster 3 is isolated, so we won't see what's happening there. But as you can see, yeah, we got some errors, but overall the transactions are still happening, although there has been a slowdown. If you remember, this number was about 150 transactions per second above. Now it went down and now it's going to go up again as everything normalizes. And same thing we can see on the second cluster. And on the console, if I reload, we should see that the third region now has 0 leaders. So all the leaders have migrated to the other regions that are healthy. And this region is not serving anything. And I mean, Emant, you can go in detail here, but I am assuming that if it stays offline for too long, it's going to be just considered completely lost. The other thing I wanted to show you, we have a global load balancer in front of these clusters, and these are the health checks. I'm expecting one of these health checks to start failing pretty soon, but for now they're still showing green. Oh, here we go. Some of them are starting to fail. Only one should fail. I don't know why two. In this case, I'm using Route 53 as my global load balancer. So back to Yugabyte. As you can see, the healthy clients have kept working with the database, even if a third of the database went down, essentially. Herman, do you want to add anything before I start the recovery?
No, I think you showed the load balancers and the user tablets. So yeah, please continue.
Okay, so one thing to point out, we generated a disaster. We took offline an entire region, and we didn't have to do anything on our software, right? The software automatically understood that there was a problem and automatically reacted to it by migrating these peers, these leaders. So now we're going to restore the connectivity, and what we would like to see is that all the available capacity now returns of online, and all of the database, even the third region, starts serving traffic again. So to recover, I have to run this command. Now this re-enables traffic to that region. This one I'm expecting, see, we didn't get any additional log out of this. We may have lost the connection to this pod, but if we recover the connection, we will probably see a ton of errors here. And here everything is fine. During the recovery, I have not seen in the past any errors, or sometimes maybe one here. But during the recovery, everything is pretty smooth. And so let's go to see what's happening to the leaders. As you can see, they are starting to migrate back. So that means the newly repaired zone is now starting to take some leaders of these tablets, and Yugabyte is trying to evenly distribute all of the leaders across the availability zones. So as I refresh the screen, more and more are migrating back. So you can imagine there is a lot of traffic and a lot of work going on between these, between all of the instances of the database.
One point to note. One point to add here is that in case of a particular node or a region goes down, the rest of the nodes wait for about 15 minutes before kicking it out of the consensus, right? So until then, if it joins within 15 minutes, which is the case right now, it will be brought back up, and the data will be replicated to these nodes, and it will become consistent.
Okay. So that concludes our demo. In about 5 minutes, all of this will be completely rebalanced. So I'm going to give control back to you, Hemant.
Sure. Okay.
All right. Yeah, our last slide has some references if you want to go deeper on these concepts. The first is the link to the white paper. The other ones are a series of blogs that we wrote around implementing these architectures with various stateful workloads and OpenShift and various cloud providers, like I said before. So you can click those links, and if you're interested in Kafka or Yugabyte, you can, as you can see there, you will find instructions and step-by-step tutorials. I think that concludes the presentation part of today. Thank you.
All right, great. We do have some time for question and answer. So if you've got a question, please go ahead and get it on in. We've gotten some good ones in so far. So we'll go ahead and get started, and we'll just see them as they come in. The first question, what is the minimum recommended network latency to manage a distributed database of YugabyteDB, Yugabyte database?
Minimum recommended network latency. Okay, so probably the question is more about like with what kind of latencies YB can work. So YB can handle the latencies up to, I mean, even if there is a large latencies up to 100 milliseconds or 150 milliseconds, YB can work, although there will be a higher write latency because you will have to replicate the data across the network. The minimum latency, I'm not sure if I'm getting it correctly, but yeah, it could be, I mean, we are happy to have a less network latency. So whatever is minimum, we would definitely work with it.
All right.
I want to take a stab at this question too. So latency is about how long the single transaction takes to be completed, right? So one thing to note about these distributed workloads is while a single transaction may be slow or fast, and we're going to talk about that in a second, these workloads can scale horizontally as much as you want. So the throughput is almost independent of the individual latency of a single transaction. So you can have as much throughput as you want. This is not true for older generation monolithical databases. Now, for the latency, as Eamon said, for a read kind of transaction, there are many optimizations that you can do. So even if you have a very high inter-failure domain latencies like inter-region or inter-data center latency, you can optimize a lot the reads. For the writes, there needs to be a communication across. So the writes are influenced by the latency that you have between your failure domains. Normally, correct me, Hemant, if I'm wrong, but normally what you can expect is to have to double the best latency that you have between two failure domains. So if you have a failure domains where the transaction is occurring and the failure domain that is close to it and the failure domain that is far from it, the latency that you can expect is the double of the latency between the two failure domains that are close to each other. So then at that point, you can make a prediction about how much latency you're going to get on a single transaction. Then it's up to you to decide if your use case can live with that latency, is okay with that latency.
All right. Wow. Great answer there. Thanks very much. Next question here. How can the write latencies be reduced in case of multi-region deployments?
Yeah, I think I talked a lot about the reducing read latencies, but this is a fair question because write latencies, reducing the write latencies would mean that either we write less or something like that. But for every write, if we have to be consistent and if we have to honor the failure domains, we will have to go to another region and write the record there. And unless that is done, we cannot say that the transaction is successful. So let's say a write comes, we go to the all the failure domains, write the data there, and come back. Right, that latency will be there, and that latency ensures that the data is consistent across these regions. And in case of a disaster, you will always be able to recover and have the consistent view of the data. So yeah. I think that is where the write latencies will be there in the picture.
Excellent. All right, guys, it's about 9 minutes to the top of the hour. We still have enough time for a couple more questions, so we'll keep plowing through. But if you have a question, please feel free to send it on in. Even if we don't get to your question, please know that folks at Red Hat and Yugabyte will be getting a copy of all the questions that came in. So I'm sure they'll be happy to follow up with you offline and get your question answered. Okay, next question here. Is YugabyteDB mature enough to replace my Oracle implementations?
YugabyteDB, I think, is being trusted by multiple customers. It is being used in multiple different verticals as well. We have customers who are inside the banking domain, inside the customers from retail domain, in the telecom domain. We have multiple customers who are trusting us. So yeah, I think if you talk about maturity, Yugabyte has matured a lot in last few years, and we are being trusted by our investors a lot to deliver a good product, and that is what we are doing right now. So I think Yugabyte is mature enough right now.
All right, great. Next question. This is an interesting one. How is split brain avoided in the event of a failover?
Well, maybe these are two different things. When a failover happens, or maybe they are one and the same thing. So when a failover happens, we cannot avoid a split brain because a split brain is part of this network. So if there is a split brain and some of the nodes are in one side of the brain and other nodes are in the other side of the brain, all we can do is detect this split brain and take the right action. So the nodes, the raft consensus algorithm that we use internally helps us in ensuring that the split brain situations are taken care of, and we serve the data only from the node in which side we have the consensus available. If in both of the sides, if the consensus is available in only the other side of the brain, we will not serve any reads or writes from the one which does not have the consensus, and we will only serve the reads and writes from the part of the split brain which has the consensus. So the raft consensus algorithm comes in, helps us here in taking this situation.
All right. Great. I think we have time for one more question here. Next one. What about non-SQL data? Can YugabyteDB work with that as well?
Yeah, YugabyteDB supports two different APIs. One is a SQL API, which is PostgreSQL compliant. So that is what I think the demo that Rafael showed. It was a TPCC client accessing YugabyteDB via a SQL API. There is another API that we support, which is the CQL API. It is the Cassandra query layer thing. And this this Cassandra query layer, Cassandra query API can be used to ingest the data like you ingest in Cassandra. We have some extra features on and over above, I mean over and above what Cassandra provides. For example, we still provide write consistency, which Cassandra does not provide with this API. But you can use SQL API for ingesting the data that is non-SQL or kind of your log data or that kind of data.
All right, great. Well, we are about 5 minutes to the top of the hour, so that's pretty much all the time that we have for question and answer period. I am going to leave the Q&A section open, though, to see if we get any last-minute questions that come in. And then meanwhile, I do want to quickly remind the audience that today's event has been recorded. So if you missed any or all of the event, please know that you will have the opportunity to access it later. Following the event today, we are going to be sending out an email that contains a link to access the webinar on demand. The webinar is also going to be living on the DevOps.com website, so you can always go look for it there. Just go to DevOps.com/webinars and look in the on-demand section. It should be right there waiting for you. Also, I do want to point out that today's slides are actually in the handout section, so please feel free to download them before the end of the webinar if you feel so inclined, and that way you get the goodness from the slide deck. And also, oh, we have a drawing for 4 $100 Amazon gift cards to get to. So why don't we go ahead and do that real quick? Our first winner today is, Kevin C. It's Kevin with a K-A. Congratulations, Kevin. Our second winner today is Harris A. That's Harris with a 1 R. Lots of interesting spellings today. Congratulations, Harris. Our third winner today is Samantha L. Congratulations, Samantha. And our fourth and final winner today is Tom H. Congratulations, Tom. We'll be following up with all 4 of you offline to get your Amazon gift card over to you. So please check your inbox. And if you don't see anything there, please check your spam folder. Haman and Raphael, great presentation. Lots of interesting, information imparted. I love watching the demos and seeing how the technology works. So I do appreciate that as well. So in judging from the comments that came in from the audience, I know they got a lot out of it as well. So thank you both very much for that. And I also want to thank the audience for joining me today. This is Charlene O'Hanlon, and I am signing off. Have a great day, everybody, and please, whatever you do, stay safe.
Thank you.